Welcome to today's lecture on proportions. I'm Drew Collop. In today's lecture, we're going to continue on from where we left off with ratios, and we're going to apply that to proportions. Let's talk about what a proportion is. A proportion is an equation of two ratios. So here, if I have ratio A compared to B and C compared to D, I can create that into an equation. A is to B as C is to D. And just like before, when we can convert our ratio into a fraction, we can do the same thing. So this ratio here, A is to B as C is to D, is equal to A over B is equal to C over D. This is a proportion. It states two ratios or fractions are equal. This here is a very important concept to understand when we get in the laboratory. Let's look at an example. Write the proportion 3 is to 5 as 9 is to 15. So we write it as a ratio, 3 is to 5 as 9 is to 15. Is that correct? Can we simplify down 9 compared to 15 down to 3 compared to 5? Yes, we can. To set this up as a proportion, I would like to set up a fraction of this. So this is equal to 3 over 5 is equal to 9 over 15. These ratios and these fractions mean the same thing. When we are working with proportions, it is important that this statement is true. These values must be equal to each other. So let's review equivalent fractions. What we learned in equivalent fractions, if we want to know if two fractions are equal, remember one method we said we could do? We could cross multiply. So we can multiply A with D, the numerator on one, and multiply that by the denominator of another. And then we multiply the denominator on the first one multiplied by the numerator of the second one. If those values are equal, then they are said to be proportional. Before we called this equivalent fractions. Let's look at an example here. Is 4 over 7 proportional to 5 over 9? So let's cross multiply. We'll multiply the 4 and the 9. We'll multiply the 7 and the 5 and see what we get. 4 times 9 is 36, and 7 times 5 is 35. So they are close, but they are not equal. They are not proportional. Let's try the next one now. This one looks different. We have a fraction within a fraction. We do the same thing. Is 2 over 1/3 proportional to 30 over 5? So again, let's cross multiply, and we'll see if they're equal. Yes. 2 and 1/3 is equal to 30 over 5. They are proportional. I'd like you to try the next two on your own. Please cross multiply and see if these are proportional. Alternatively, what you could do is also simplify them down to lowest terms and see if they're the same, or you could find a common denominator and see if the numerators are the same. 3 different methods to do the same thing. Let's take them up. 0.5 times 20 equals 10, and 4 times 10 equals 40. Therefore, no, they are not proportional. Let's show you the other methods as well. 0.5 over 10 and 4 over 20. Let's get them so they have common denominators. Multiply this side by 2. And in this case here, we get 1 over 20. These are not equal. Therefore, no, they are not proportional. Over here now, 3.5 times 10, 35. 6.5 times 7, 45.5. Therefore, no, they are not equivalent. Here we can get them so they are the same denominator, times 7 times 7, times 10 times 10. And here we will get 45.5 over 70, and here we will get 35 over 70. You can see that's where those numbers come from in the end. These values here, they're the numerators here. They are not equivalent fractions. Therefore, they are not proportional. How we're going to work with proportions is we're going to find a missing term. A proportion is the equation of two ratios. What we usually do in mathematics, if we have an unknown, we call it x. I'm assuming you already know this. So if we have an unknown term we want to solve, we put x in its place, and then when we solve it, we can substitute x for the right answer. So when we set up a proportionality equation, We want to rearrange it eventually so that x is on its own on one side of the equation and everything else is on the other side. We then know what x is equal to. Let's look at an example here. Solve the proportion x is to 9 as 3 is to 18. Let's set that up as a ratio first. X is to 9 as 3 is to 18. We will now convert that into a fraction. X over 9 is equal to 3 over 18. In this case here, we want to solve for x. Now to rearrange an equation, what we do is we want to try and isolate x on its own. We want to try and have x on one side of the equation and all the numbers on the other side. And then that will tell us what x is equal to. So we must now rearrange the equation. What we do is we always do the opposite of what we have in the equation. You can think of it as a balancing act. In this case here, I'm dividing by 9, so I want to do the opposite. I multiply by 9. Now if I multiply by 9 here, this side gets weighted down. So to make sure it stays level, I must multiply the other side of the equation by 9. You can think of the fulcrum here as the equal sign. If I multiply that side by 9, everything stays in balance. I haven't changed any values in this equation. I've just rearranged the equation. Now, some of you might think of this as I'm moving the 9 to the other side, but that's the reason why it works, because you're multiplying both sides by 9. When you do that now, I have a 9 on the top and a 9 on the bottom. The 9s cancel out. I'm left with now x is equal to 3 over 18 times 9. Let's work that out now. Simplify that down. 1 9, 2 9s. And here we get 3 over 2, which you could write as 1.5. In this case here, 1.5 compared to 9 is equal to 3 compared to 18. X is equal to 1.5. You should start getting very comfortable with solving for x and rearranging. Again, if you're having problems rearranging, maybe because somebody taught you this silly little symbol here, please forget that. It was a crutch and it will hold you back. Let's solve this proportionality statement, solving for x. 5 is to x as 30 is to 50. 5 is to x as 30 is to 50. Let's set that up as a fraction. 5 over x is equal to 30 over 50. Now you can see this is a bit different compared to what we had from before. In this case here, x is in the denominator. But we can also rearrange it. What we want to do here, let's move the x to the other side. How do we do that? Multiply both sides by x. In that case there, the x's cancel out. I'm now left with 5 is equal to 30 divided by 50 times x. Let's do this one step at a time. Let's move the 50 over to the other side now. How do we do that? I take this whole expression, I'm dividing by 50, so I multiply by 50. Do the same thing over there now. The 50s cancel out. 5 times 50 is 250, and now I have 30 times x. You also might see that as 30x. Remember, when we don't see a symbol between a number and a bracket, we assume it's multiplied. The same holds true when there's a number in front of a variable. X is a variable. So in this case here, I want to get rid of the 30. In this case here, I'm multiplying by 30, so I divide both sides by 30. And you can see 30 on the top, 30 on the bottom, they cancel out. Over here, I can take a 10 out of the top and the bottom by canceling out one of those zeros. And then I have 25 over 3 equals x. It doesn't really matter on what side you have the variable and the number. I prefer to have it on the opposite side. We can switch these directly. It doesn't change anything over. So we can say x is equal to 25 over 3, which if we converted that to a mixed number, it would be 8 1/3. Final answer. So what we're doing now is we're taking what we've learned about fractions, what we've learned about ratios, and we are starting to introduce what is known as algebra. We are solving for an unknown. So here is more of a word problem. Sue earns $7.95 in 5 hours. How much will she earn in 39.25 hours? Solve. Here we have to build our ratio first. $7.95 is proportional to 5 hours, and that is equal to Now, we don't know how much this person's going to make, so that is our unknown. And we know they worked for 39.25 hours. That's a criminal wage. Let's adjust this a little bit. Let's say she earned $79.50 in 5 hours. That seems a bit better. Now let's solve this. What do we want to solve for now? We want to solve for our unknown. Our unknown is how much money that Sue made after working 39.25 hours. We have a bit of information. We know how much she made in 5 hours. Let's do some math to find out how much she made in a much longer period of time. Let's turn that into a fraction. And notice I'm leaving the units in there. Also notice we have the same units on the top and we have the same units on the bottom. This is a check to make sure you're doing it correctly. What do we want to do now? We want to try and isolate X on its own. X dollars is being divided by 39.25 hours. So because we're dividing, we'll do the opposite. We'll multiply this side by 39.25 hours, and we will do the same to this side. In doing so, you can see the number cancels out, the units cancel out. Over here, same thing. You can see hours and hours, therefore the hours cancel out. That's why the units disappear. Let's now multiply 39.25 by our $79.50 to find out what do we get. And that's equal to X dollars. Let's solve for X now. When we're working with money, what do we round off to? We round off to the nearest 2 decimal places. So this would be $624.08. Therefore, Sue made $624.08 working 39.25 hours. Now ask yourself, does that sound reasonable? After 5 hours, this person made about $80. And after 39 hours, that's quite a bit more time. And you can see that's quite a bit more money. So this does sound reasonable. Let's try another problem. Let's say we want to make some orange juice. It says here, if we want to make fresh orange juice, we can squeeze 3 oranges, and from that, we get about 1/3 of a cup of orange juice. So how much juice can we expect to obtain from a bag of oranges, and a bag contains 24? Let's set up our ratio first. 3 oranges makes 1/3 of a cup. I'll just call it OJ. This is equal to, now you can see how I set this up. I have oranges compared to cups of orange juice. So let's set up the same over here. We're going to have a certain number of oranges, and it's going to make a certain number of cups of orange juice. What do we have here now? We're given 24 oranges, so I can write that in here. What I'm not given is how many cups of orange juice that makes. That's what I'm trying to solve. So I will put in X here to represent the unknown. Let's now convert this ratio into a fraction. 3 oranges divided by 1/3 of a cup of OJ, and that's equal to 24 oranges divided by X cups of orange juice. You can see here we have the X on the bottom. So what I will do is I will multiply both sides by X cups of orange juice to get rid of that. Let's see what we have on the bottom over here. Over here we have 1/3 of a cup of orange juice. Let's move that to the other side. By doing that, I will multiply both sides by 1/3 of a cup of orange juice. Let's see what happens here now. You can see we have 1/3 of a cup of orange juice here, 1/3 of a cup of orange juice there. It cancels out. We have X cups of orange juice here, X cup of orange juice there. Those cancel out. Notice what we've done is we've moved this to the top here, and we moved this to the top here. This is sometimes known as cross multiplication. Some of you know this technique already, but you do this too often. You can only cross multiply when you have two fractions that are equal to each other. Let's see how we can speed things along here and simplify it. I'm going to erase this. So again, we have 3 oranges compared to 1/3 of a cup of orange juice, and that's equal to 24 oranges compared to X cups of orange juice. What I'll do now is I will cross multiply. If I just work with the numbers here and I cross multiply, this gives me 3x is equal to 24 times 1/3. Let's multiply those together here. 3x is equal to 24 divided by 3. 24 divided by 3 is going to be 8. And then we want to isolate the x on its own. Divide both sides by 3. 3's cancel each other out. We work that out. We get x is equal to 8 over 3, which as a mixed number is 2 2/3. Now, what are our units on this? Notice I remove the units when I switch from here to here just to try and save space. What I can do, I can take this and I can look up here. X is the number of cups of orange juice. So therefore, 24 oranges make 2 2/3 cups of orange juice. Let's build on that. Let's say I'm having guests over and I need 8 cups of orange juice. How many bags of oranges do I need to buy? I need 8 cups of orange juice. How many bags of oranges do I need to buy? Previous question here, we could see that 3 oranges makes 1/3 of a cup of orange juice. So we can use this to find the answer. Let's try that now. 3 oranges makes 1/3 of a cup of orange juice. Over on this side now, I need 8 cups of orange juice. So down below, I need 8 cups of orange juice. How many oranges do I need? We'll say that's X oranges. Let's cross multiply here. We get 1/3 X is equal to 3 times 8, which is 24. Here we are multiplying by 1/3. So we will divide both sides by 1/3. The 1/3s cancel out. And we're left with 24. Now we're dividing by 1/3, which means we flip and we multiply. So here we get X is equal to 72. 72 what? X was oranges. 72 oranges. Is this our final answer? No, it's not. Why? Because I didn't ask for how many oranges. I asked for how many bags of oranges. So now we have to convert from number of oranges to number of bags of oranges. Let's do that now. What was I told earlier? I was told that a bag of oranges contains 24 oranges. So we'll use that. So 1 bag is to 24 oranges. Over here, I have 72 oranges. Let's call this X now. We want to determine how many bags we need. Again, we'll cross multiply. 24X is equal to 72. Divide both sides by 24. And X is equal to 3. Therefore, 3 bags of oranges makes 8 cups of orange juice. As you can see, we're combining fractions that we learned earlier with algebra, solving for an unknown. I'd like you now to practice some of this on your own. I'd like you to do A through to G. Stop there. H onwards, there's a bit more information I need to cover with you. So pause your video and work on A through G. Here's A, B, C, D, E, F, and G. So pause your video, give these a try. So here's your answers. Let's take some of them up. 8 is pretty simple. I'm going to leave that for you. Let's take up B. Sometimes what's useful in math when you have a word problem is to draw a little picture of what's going on. So let's draw a picture. We have an 8-foot light pole. Here's the ground. Here is a light pole. A light on the top. And this is 8 feet tall. It says it casts a shadow of 14 feet. What does that mean? Well, here's our sun. And the sun's rays shine down, and it casts a shadow. So here's our shadow of our light pole. And we say this is, let's draw a little shadow here of it. And it says that this shadow is 14 feet. Here we have a nearby tree. And this tree also casts a shadow. Caused by the sun. And we know this shadow is 56 feet. The question is, how tall is this tree? Let's remove the question mark and we'll put in our value of x, our variable. You can actually do this. This actually works. If you want to know how tall something is, find something that's near it, measure the shadows, and then you can do this and you can find out how tall something is. So let's set up that equation. So an 8-foot light pole makes a 14-foot shadow. So 8 feet compared to 14 feet. Over here, the height of the tree is what we want to know. That is our x value. And over here it says it makes a 56-foot shadow. Let's get rid of the 56 by multiplying both sides by 56. You can see these cancel out. I'm now left with x is equal to, in this case here, 56 times 8 divided by 14. X is equal to 32. What is our units? Well, here we're talking about x feet. So therefore, the tree is 32 feet tall. Final answer. Notice if you take the units out when you do the calculations, usually I want to leave it in, but here it can be confusing. Make sure you put it back in at the end. If I said the tree was 32 tall, 32 what? 32 feet, 32 centimeters, 32 miles. The units makes a big difference. And if you're having a hard time conceptualizing some of these word problems, especially in physics class, it's all word problems and you have to try and figure out what is happening. Draw yourself a little diagram to visualize it. So just like we were able to use something that was proportional, the lamppost beside the tree was having the same angle of sunlight being shone down on it, so it could cast the same shadow. The shadows were proportional. Let's now solve these two proportional triangles. So these are proportional. I can say 5 is to 2 as x is to 10. This is your left side, and this is the bottom. These two things are proportional. Now we can solve it. We can cross multiply. 2x equals 50. Divide both sides by 2. The 2's cancel each other out. X equals to 25. Therefore, we have now solved for x. D and E I don't think are a problem. I'm going to skip over those. Let's take up F. A computer server transmits 10 web requests in 2 seconds over the internet. How many requests can the computer serve in 1 minute? So if I was to set this up, 10 requests compared to 2 seconds is equal to X number of requests in 1 minute. Do you see the problem with this one? Remember, when we're setting up two ratios, the units have to be the same. Those are not the same. One is in seconds and one is in minutes. It doesn't matter which one you convert it to. I can convert them both to seconds or both to minutes. Because I think minutes is easier, I'm going to say, well, we know that 1 minute is 60 seconds, so I can just swap that out and put in its place 60 seconds. Now you can see I have the same unit on both. Let's set up that fractional proportionality statement. We can cross multiply, divide both sides by 2. Therefore, 300 web requests can be processed in 1 minute. So notice here we had to do a conversion so that they were the same units and they would cancel each other out. I think G is pretty simple too. Just remember, when you're dealing with money, you round off to 2 decimal places. Let's look at H now. We're going back to orange juice now. To make orange juice from frozen concentrate, you use concentrate to water at a ratio of 1 to 3. I don't know if you've ever done that before. It's a can of frozen goo, and you dump it out into a container, and then it says mix that with 3 equal cans of water. And then you have orange juice, but not freshly squeezed. It's much cheaper. We use 1 can of the concentrate, and then we add 3 parts water to that. The question is how much concentrate and how much water do you need to make 1 liter of orange juice? Answer in milliliters. Let's examine the things that are in this question. We have the concentrate and we have water. And it says 1 part concentrate, 3 parts water. But what are we making here? We're making orange juice. When I mix the concentrate with the water, how much orange juice does it make? We add those together. It makes 4 parts orange juice. 1 part concentrate plus 3 parts water makes 4 parts orange juice. You need to understand this. You have to combine these together to make a third number. That is how you answer these last problems. Let's try this now. So I'm asked to find how much concentrate and how much water I need to make 1 liter of orange juice. So let's say we're going to solve for X number of liters of concentrate. Divide that by 1 liter of orange juice. Over here, we'll have concentrate on the top and we'll have orange juice on the bottom. And it says for every 1 part concentrate, it makes 4 parts orange juice. We'll cross multiply the numbers. 4x equals to 1. So x is equal to 1/4. X is 1/4. What's our units here? Right here. X equals to 1/4 liter of concentrate. Is this what I asked for in the final answer? It is not. I asked for it in milliliters. What's 1/4 of a liter? Well, a liter is 1,000 milliliters. What's 1,000 divided by 4? It's going to be 250 milliliters. So that's how much concentrate we need. Now we could go through and we could do this whole calculation now for the amount of water. X liters of water over 1 liter of orange juice equals, we have 3 parts water for every 4 parts of orange juice. But we don't need to do all this work. You can if you want to, but notice this. What is our final volume going to be of orange juice? It's going to be 1 liter. If 250 mils is concentrate and the rest is water, then how much is water? 1,000 mils total, the 1 liter, minus 250 mils of our concentrate. So this is our orange juice and this is our concentrate. Subtract those away, 750 mils of water is required. Therefore, mix 250 mils concentrate with 750 mils of water to make 1 liter of orange juice. I'd like you now to try I and J on your own. I'm not going to take up I and J. I have the answers here. I will give you a hint if you had a problem here. The recommended ratio of gas to oil is 25 to 1. What are we making? We're making fuel. So 25 parts gas plus 1 part oil makes 26 parts fuel. Again, we have to combine those together to get our new final volume. If you have any problems with that, you can contact me via email, or you can ask your question during tutorial. Same holds true here. We're making a furniture polish. Combine lemon oil and mineral oil in this ratio. So here we have 3 parts lemon plus 200 parts mineral oil, and that makes 203 parts of furniture polish. And we're asked how much lemon oil you need to make 10.15 liters of furniture polish. When you work it out, you should get 150 mils. Let's bring this round to chemistry. Let's talk about what an alloy is. An alloy is a mixture of 2 metals. Oftentimes an alloy is stronger than the original 2 metals together. Why? Well, maybe we have copper atoms and they are spread out like this, and we have tin atoms and they're spread out like this. When we mix them together, it fills in the gaps and makes it stronger. This is an alloy. An alloy is a mixture of metals. So we're going to use exactly what we learned earlier about mixing things together and finding the new final volume, and we're going to apply it to chemistry. We're talking about bronze. It's an alloy. You mix together copper and tin in this ratio, 23 to 2, copper to tin. The first question is, what mass of each metal is present in 100 grams of alloy? Let's work out copper first. We want to know how many grams of copper is in 100 grams of alloy. And what do we have here now? You can see when we're making our bronze, we have 23 parts copper, 2 parts tin, and that makes 25 parts bronze. Here we want copper on the top and our alloy on the bottom, just as it is in the other fraction. Here, every 23 parts copper makes 25 parts alloy. We cross multiply, 25x equals 2,300. We then divide both sides by 25. And we have x is equal to 92 grams of copper. So that's how much copper is in 100 grams of alloy. Now to solve for the tin, we could do the same thing. Just swap out copper here for tin. This would be 2 parts over 25. But there's an easier job we can do here. We have 100 grams of alloy, and we subtract the 92 grams of copper. The only thing that's left is the tin. This makes 8 grams of our tin. There's often easier ways to solve this problem if you think about it from a different standpoint. I'd like you now to try 2 and 3 here on your own using what we learned earlier. 23 parts copper plus 2 parts tin makes 25 parts alloy. See if you can solve these on your own. Okay, let's take this up. Again, if you're having difficulty, let's draw a little diagram here. Here is our copper, and here is our tin, and here is the bronze we're going to make the alloy. And what we do is we mix in the copper and the tin together. We take 23 parts copper, 2 parts tin, and in the end we get 25 parts alloy. Now, this question here, it says how many grams of copper are there for 100 grams of tin? So in this example, let's say we have an unlimited amount of copper and we have a limited amount of tin. We only have 100 grams of tin. We want to use all of it up. So how much copper do I need to add to this tin to make my alloy? So here, x is our unknown. X grams of copper and we're going to compare that to 100 grams of tin. What do we have here now? Every 23 parts copper, we use 2 parts tin. Again, we can cross multiply our numbers here. 2x equals 2300. Now we divide both sides by 2. And here x is equal to 1,150 grams of what? Of copper. For this one, we do something similar. In this case here, we're having 100 grams copper. There's a limited amount of copper. We want to maximize the amount of tin. We use a very similar method to the last one. Give that a try on your own. Now that's an alloy. In this one here, we're going to deal with combustion. Combustion is a fancy term for burning something. So when carbon burns, we have that much carbon dioxide is formed for every 1 gram of carbon. So we're burning carbon, and it produces that many grams of carbon dioxide. How can it produce more? If I only have 1 gram of carbon, how can I produce more than 1 gram of carbon dioxide? Carbon is C, carbon dioxide is CO2. When we're combusting carbon, it reacts with the oxygen in the air and makes a new molecule, CO2. So that's how we can increase the mass. We're not actually increasing the mass remains the same. It's just we're combining them together. That's what happens when we combust carbon. It makes carbon dioxide. Now let's look at our problem here. 9.06 grams of carbon are consumed. How much carbon dioxide is produced? With the information given, we know 3.664 grams of CO2 is made from 1 gram of carbon. These things are known. We can use this now to convert grams of carbon to grams of carbon dioxide. Here we are given the amount of carbon. We want to know how many grams of carbon dioxide are produced. So let's say X grams of carbon dioxide over 9.06 grams of carbon. Here now, we'll use this to build the next fraction. We put CO2 on the top, carbon on the bottom. 3.664 grams of CO2 is produced for every 1 gram of carbon. We cross multiply now. 1x is equal to 9.06 times 3.664. That's equal to 33.19584. Please write down all those numbers. Very important. Do not round off until the final answer. Here's the final answer here. We'll say it's 3 significant digits. So what we do when we round off, we're going to round off to 3 significant digits. I look at the number beside it. It's greater than 5, so this rounds up. So this is approximately equal to 33.2 grams. Of what? Of carbon dioxide. So every time I burn 9.06 grams of carbon, it produces 33.2 grams of carbon dioxide. Don't worry about significant digits for now. We're going to cover this in a lecture very shortly. I'd like you to try 2 and 3 on your own right now. Pause your video, give them a try. Going to make one modification here. My apologies. I'm going to make that 4.0. Doesn't matter for today. I haven't taught significant digits yet, but we're going to get there eventually. If you look back at the notes, I want to make sure you can understand why we did that. Let's take this up now. Here we have 4.0 grams of carbon are consumed. How much carbon dioxide is produced? This is exactly the same as the other one, so I'm not going to take this one up. If 11.01 grams of carbon dioxide are formed, how many grams of carbon must have been consumed? So I know this. I want to solve for this. So X grams of carbon over 11.01 grams of carbon dioxide, and that's equal to, what was our fraction from up above? Well, in this case, I'm going to put carbon on the top, and I'm going to put CO2 on the bottom. Why? Because I have carbon on the top here, and I have CO2 on the bottom there. And we know from up above, 1 gram of carbon makes 3.664 grams of carbon dioxide. We then cross multiply. 3.664x is equal to 1.01. And then we divide both sides by 3.664. Those cancel out. And we're left with here x being equal to 3.004912664. Let's talk about rounding for a moment here. I'm going to round this off to how many significant digits? I'm going to round it off to 4. Why? Because the number here was given as 4 significant digits. We'll cover this in more detail later on. So 1, 2, 3, 4. I look at the number beside that. It's a 9. So this rounds off to 3.005 grams. Don't worry about significant digits for now. That's a problem for another day. So today we took our concept of ratios we learned about last day, and we tied it into proportionality, building an equation. I introduced the concept of the unknown, calling it x, and we looked at rearranging equations and solving for x. Hopefully you can see from these last problems how this technique might be useful to you in the laboratory. That's all for today. Until next time.